Okay, thank you so much. I appreciate it. The presentation that I'm going to talk about, mainly I'm talking about transportation, electrification. I'll talk a little bit about how we can design very efficient system-level solutions for future automotives. And then at the end, I will conclude the presentation with talking a little bit about other research areas that our group is involved and might be interesting. So briefly, in the introduction, I'll talk about transportation 1.0. What is it called? Why people call it 1.0, 2.0. I'll talk about power electronics' role in this transportation sector. What are the DOE's, Department of Energy's technical goals, and how we can target those and achieve those targets. Then a big part of this presentation will be focused on designing isolated level 1 and level 2 chargers for next generation of electric cars. Then I will talk a little bit about integrated onboard chargers as an alternative solution to increase the power density and reduce the size and weight of these converters. And then I will conclude the presentation by talking about hybrid energy storage systems which are applicable to vehicular systems. And I will talk about energy harvesting, a little bit about our activities on energy harvesting, free and human body motion, and mention about recent activity that we have started and are continuing on the miniaturizing power electronic interfaces for micro-robotic systems. So transportation 1.0, since 150 years ago, internal combustion engine has been the driving force behind majority of our vehicles. Starting from electric cars, from internal combustion cars to motorcycles to ships and so forth, and even aircraft. I'm sorry?
About trains.
Trains also, they're majorly, they have their own concurrent. So all the kind of transportation, it's been internal combustion engine. And there are a huge market in this area. Looking at the current statistics going on, you see that there are 900 million vehicles on the road in the world, and there are over 250 million in the US. And the interesting thing is that there are 15 million new vehicles are being manufactured every year in the world. And the current economic growth in countries like China, India, and elsewhere is going to add to this market. So the market is going to get bigger and bigger. But what is the problem with this system? First of all, this transportation 1.0 accounts for 40% of the greenhouse gas and 70% of total emission. And the interesting thing is the transportation 1.0 is 99% dependent on one source of fuel, which is petroleum, which is not sustainable, right? There are current concerns coming up because of the cost of the fuel is rising. I mean, they're saying we will gonna run out of fuel in future. Economic concerns, national security threats, and environmental and public health are issues which are pushing us towards a new generation of the cars, which puts us in the road to look at transportation 2.0. Transportation 2.0, in fact, is a paradigm shift from internal combustion engine vehicles to first hybrid electric cars, and then plug-in hybrid electric cars, which are also called dual fuel cars, and then finally it will end up at electric cars. And this is transportation 2.0. Now, what is the enabling technology which can walk us through this movement is power electronic, in fact, because the biggest load in the car is propulsion, right? Propulsion, charging, energy storage system. These things are not practical without power electronic. So inside the car, inside the plug-in hybrid car, we can see there are majority of the loads that are enabled with this technology. For example, a very basic one is energy storage. And then there is propulsion. And then propulsion machine and propulsion inverter. And then there is another DC-DC converter, another bidirectional DC-DC converter between the propulsion inverter and the energy storage system. And also, we need to have charger. And again, we need to have another DC-DC converter, which needs to convert the high voltage DC bus of the energy storage system to 14-volt conventional loads that we have in our conventional cars. So looking at these things, we would see there are like tons of areas, tons of power electronic parts in a simple sedan car. So the issue is these components are costly, they are heavy, they take a lot of space. Efficiency of the systems, if they are not properly designed, might be low. Reliability is a big concern in this, and packaging is a very important factor in this. Now, what are the approaches, how we can address these things? The point is, we need to first come up with novel and innovative circuit topologies, which could give us the opportunity of integrating these topologies with each other. So we can integrate them with each other and come up with new topologies. Second of all, we need to increase the power density of these devices, which could be achieved first, again, through innovative integrated topologies. Second, modular structure. Third, using wide bandgap devices like silicon carbide GaN devices to be able to increase the switching frequency of these converters, which are limited because of the usage of IGBTs or MOSFETs, and we can reduce in that way passive components. And important thing is also to try to eliminate DC link capacitors, which are one of the biggest failure components in power electronic. They are heavy and they are a point for failure. And also, as much as we could, we should try to reduce the size of magnetic components. Magnetic components are the heaviest bulk, weight, in terms of weight and size, and also they cost also a lot of money. So DOE, Department of Energy, has different targets for power electronics and traction drive systems. In fact, some people might say, oh, why DOE has two different targets for traction drive system and for power electronic? Because the fact that even inverter, the cost associated with the inverter versus the cost associated with the bidirectional DC-DC converter are two different. So achieving the cost for inverter design is easier because of the less number of components associated. Inverter, most of the cases, we don't have passive components in the inverter. However, inside the car, we would definitely need to have some, but in compared to like a bidirectional DC-DC converter, which definitely has a capacitive component, inductive component, it would be smaller. So, and these presentations are based on Susan Rogers. She's the program manager at the Department of Energy. My focus is going to be mostly focused on charger in this presentation. So these are the DOE targets for charger. And I will talk about the basics of a charger, how that's integrated in the whole system. And I'll talk about how we can achieve these numbers here. So looking at these numbers, you will see right now majority of the cars in the market, they have 3.3 kilowatt chargers, which is not practical. Assume you have an electric car and you want to charge it to the grid and charge it with 3.3 kilowatt, and your battery is 24 kilowatt hour. It will take more than 10 hours for you to charge it. So we need to have different alternatives to charge them faster. So the approach that we're going to look at it is this. We recently got like a MIPS grant, Maryland Industrial Partnership grant, to build a 7.6 kilowatt charger, and that is going to be like slightly more than 2 times power level, but our goal is to reach 2015 goal for 3.3 kilowatts. So with 7.6 kilowatts. I'll talk about, yeah.
Size do you express in liters?
Yeah, liters, they assume it in liters. We can send centimeter cube as well.
Yeah. But it's interesting that the standard way is
Yeah.
liters for fluids.
Yes, most of the time, but they're talking about. So our goal is to get a weight of less than 4 kilograms for that 7.6 kilowatt charger, efficiency of over 93%, and the cost might slightly be above. We are not right now concerned for the cost. We are mostly focusing on efficiency, weight, and size. And I'll talk a little bit about the integrated charger as well in this.
Weight and volume kind of be equivalent in terms of the things, or is one more important than the other?
No, weight is more important than volume. Weight is more volume because I'll talk a little bit more about how much. I can right now say that 14% reduction in the weight of the car overall would increase the all-electric range of the car by 17%. So weight is more important. We have, less or more, we have space in the car. Yeah.
Is it possible to relate, say, for some of the numbers here or the other ones, like the range, if you fully charge it, or within a certain amount of time of charging, roughly all these goals relative to ranges, 100 miles or whatever?
We can do that. We can definitely, depends, that mainly depends on the size of the energy storage system and the energy density of the energy storage system. However, we can kind of relate them because it depends on the time that we require to charge the car. So in fact, in our group, we are right now focusing on level 2 chargers. This might be a good thing for everybody to know. Like level 1, when we talk about level 1 charging, everything less than 1.92 kilowatt is called level 1 charging. Everything between 1.92 and 19.2 is level 2. Anything above 19.2 is called level 3 DC fast charging. And DC fast charging is kind of impractical to put on the car, on board. But level 1, right now a lot of cars, they have it. And level 2, people are starting to put. But the level 2 chargers, they're mostly limited due to the fuse size that are used. And they're, right now, most of the manufacturers, they're putting 3.3 kilowatts and paralleling them, which is not efficient at all. So I'll talk about what is our approach, which will be different than all others.
Can you explain what you mean by charger? What's the source of the energy, and then does it include the battery?
No, charger does not include the battery. The energy storage system is a battery, but the charger, when I talk about charging, I'll show you the structure of the charger, which is from anything from the outlet that we have to the battery.
So AC to DC?
AC to DC, yes.
And you assume the AC doesn't have high-frequency components, it's just...
It could be like a simple, like a grid, 240-volt industrial outlet for us, single phase. So let me a little bit talk about design consideration for isolated onboard EV chargers. Again, before I start this, we are interested in looking at different options of even putting level 3 charger on the car. A lot of people, they feel like level 3 charger on the car, impossible, maybe. But we have some ideas how we can integrate it, but that's one of the research directions that we're looking at. For now, we'll focus on this. So this figure shows like the general structure of a conventional charger. In fact, we have EMI filters just to prevent the conductive noise, and then we have AC/DC converter, we have isolation stage, and we have output filters. So conventionally, this is a conventional onboard charger for people use for level 1 chargers. So you can see there is, after EMI filters, we have a rectification stage. Then we have a boost converter, which is mostly used for power factor correction. And then we have another bridge here and another bridge there. And this part provides isolation and battery current regulation. Now, majority of these systems, they don't have resonance here, so this is a simple circuit. People are starting to look at resonancy, how to improve. If this part has a very low efficiency in conventional chargers.
What kind of frequencies?
I'm going to talk about it. We are looking at 200 kilohertz. 200 kilohertz. So, and these components would be bulky in some cases. Now, the topology that we are looking at is this one. This is a bridge. Now, this is same boost converter topology, right? But then there are two of them in parallel. Then we have this is a half bridge followed by an LLC Resonant converter followed with another half bridge and connected to only a capacitive filter, not LC filter. Now, you might look at this and say, oh, why you're using two of these things? Using two of those would increase the size of your converter, this part. But that's not true. I'll show you how using these two would further reduce the size of these inductors and the overall size, and also improve the reliability of DC link capacitor, which I mentioned is a big concern. So I'll talk. And then creating the resonance using these elements here would increase the efficiency of this converter. So in So this one, the first part, I'll just focus one by one, step by step, and then move forward, how each one would impact the system design. So first, let's assume we have these two leg interleaved boost topology. So in the boost interleaved topology, in fact, we have two of them. If we have n phases or n legs, we will be turning on and off these switches. We will be switching these legs with 360 degree over n number of the legs. If we have two legs, it's 180 degree phase difference. So depending on the duty cycle of these two switches, we could have two modes of operation, which in one case, duty cycle is smaller than 0.5. In another case, duty cycle is bigger than 0.5. So in other words, in one case, these two overlap, and in this case, these two do not overlap, okay? When the switch is on, the inductor current increases. When the switch is off, inductor current decreases. So similar thing happens for the second leg. Now, interesting thing, if you look at the current legs here, and then you add them up, the input current, which is the input to the whole system, the ripple will be very small. In compared to having only one of those boost topologies, which this is going to be the ripple, right? So let me show you something here. If we look at if we define a function like I in or delta I in over delta IL, in the case of single phase boost is 1, right? Obviously, because delta I in is equal to I inductor. However, in the interleaved, it's going to be dependent based on these equations. And if I plot them, if I plot the inductor current ripple versus input current ripple and versus inductor current ripple, I will see that this is for the interleaved topology, that is for boost topology. So now, reduced inductor ripple will help me to reduce the total harmonic distortion of the system, and reducing total harmonic distortion in the input current would help me to reduce the size of these magnetic inductors. It's been shown, I'm not going to prove it here, but if we do this, in fact, for the same power and energy level, we could reduce the size of the magnetic component by 32%. As opposed to using two inductors, as opposed to using one inductor, they can reduce the size by 32%, and that would help us increase the power density. Now, another important factor is to look at the effect of this interleaving on the output DC link capacitor. So what is the current which flows through this DC link capacitor? Is in fact the current ID1 plus ID2 minus IO, right? That's the current which will flow there. Now, and if you write the equation and look at the turn on and off as these switches, depending on those two cases, we will have these two currents flowing through the DC link capacitor. And DC link capacitor should be able to filter these ripples. Now, the interesting thing is if we, based on these are the equations which shows that, if we can operate this system with duty cycle equal to 0.5, we would notice that at that case, the amount of the current which is going inside the DC link capacitor is much smaller. It's only the ripple on the inductor current, which we have controlled to operate in continuous conduction mode. So smaller the current going through DC link capacitor would in fact reduce the Ri squared losses, right? Ri squared losses include, so will reduce the thermal burden on the capacitor and will improve the reliability on the capacitor. We haven't studied how much improvement in terms of analytically, say, for example, it will increase the reliability capacitor or life by 30% or 20%, but that's something that we would look at it. But we know that would improve it. Now, looking at here, and 0 duty cycle and 1 duty cycle, which are almost impractical, we cannot get 0 or 1. We can get very close to 0, very close to 0.1, but not 0. If we can operate this again at 0.5 duty cycle, we would almost get very, very little ripple, and which needs to be filtered with the DC link capacitor. So that's also another advantage. Yep.
If 2 is better than 1,
Might be, it might be, but however, the control also will be complicated there. For our purposes, it's good enough for us to deal with 2, with the control of 2, and then stick with 2. But I think it's not very much practical to go with 4 of them in parallel with them because the control will be complicated, the system, and also it will cause. We need to look at it. I mean, see how exactly.
Good enough. It means that you can meet the DOE.
Yes, the target that we want to look at. I think the tool will help us to meet that target. Yeah, that's right.
Just following up on, is there any sort of design optimization you can apply here so that the number 2, 4, whatever is the thing you decide on, obviously it's the integer, but you're taking into account the control aspects as part of an objective as well as these other things, so that you don't say good enough. You
Okay.
say, given the current trade-offs that I'm looking at, 3 is best, or something like that.
That's fantastic. I mean, I think that's very useful to us. We could look at that kind of.
Shapur Zarman and I have been doing for ONR actually.
Oh,
We look at kind of robust optimization.
Okay.
You're doing it too, I think. And anyway, just following up on his question.
sure. I mean,
Maybe there's a way to
Definitely.
improve it a little bit.
definitely we can definitely work together and come up maybe with different answers, saying like the 3 level is better than 2 level,
Yeah,
or 4 level is better than 2 level. So, moving forward from interleaved part, the second part is the resonant, series resonant part that we mentioned. As opposed to having 2 different layers, we will use this resonant. Oops, sorry, this resonant topology. In fact, depending on first of all, there are 2 resonant frequencies. There's a primary resonant frequency, which is resonance between LR and CR, defined at primary resonant frequency, and the other one including the magnetizing inductance of the transformer, and that's called the secondary resonant frequency. Depending on the relationship between the switching frequency of this converter and F0 and F1, there are going to be 5 different modes of operation for this converter, which if I want to explain those things, would take like much longer time. But I will only focus on explaining this mode because this is the mode that basically we're interested in, and I'll explain why we are more interested in this switching frequency. So in this switching frequency level, when switching frequency is less than F0 and more than F1, and if S is close to F0, there are going to be 4 modes of operation in this system, but I'll explain 2 of them. The other 2 are exactly similar. This mode starts, in fact, by we turn off this switch S4 at a finite current and finite voltage. So that is hard switching. Hard switching is the case that there is still a current flowing through the switch, or there is voltage across the switch, and you turn it off, losses will appear there. So as soon as this on, the current flowing through this will enforce D3 to turn on, and that's also hard switching. Again, we don't like these conditions to happen, but some cases it is impossible to prevent hard switching. So this happens, and then now what happens? This diode conducts in the same time. The output voltage will be across this magnetizing inductance. So there's a constant DC voltage, assuming that the DC output voltage is tightly regulated enough. Then the resonance happens between these 2 components. The resonance will happen between these 2, and the voltage and the current ILR which was negative at the beginning, will start to rise. It will rise, and at some point, it will become positive. So I can start triggering this switch at the beginning of the mode, and as soon as the current passes the zero becomes positive, this will turn on. Now, turning on of this switch is zero ZVS, zero current switching, and 0 voltage switching. So turning on of it will be no losses associated with it. And so this is the equivalent circuit. Shows that this is the VDC applied here, and that's the equivalent circuit from the outside. And so I'm sorry. Okay. Yeah, I mean that happens in this point. In fact, we turn that mode 1 starts from this point to this point. We turn this one on. This also turns on. So at this point, you can see the voltage and current through these switches are finite time, right? So the hard switching will happen. And at this point here, I can turn this switch on, and this diode will be off. right? So then this mode 3 ends, and this current, the current which is going through this magnetic component, because there is a constant voltage across it, will linearly increase. So this is linear increase, and that is resonant, right? As soon as these two currents become equal, this diode will turn off. This diode will turn off at this mode, and mode 2 will start at this point. Now, in mode 2, which is like this part of the circuit is completely isolated from the other side of the circuit. This is the resonant system. So this capacitor here, the resonant capacitor, will resonate with the leakage inductance of the transformer and magnetizing inductance of the transformer. And that will end when the mode 2 will end whenever we turn off the switch, S4. So that second part also will happen in finite current and finite voltage. You can see this is, and then it will again continue the same thing. So these two modes are similar to these two modes. So this is the way that the switching system will happen in these modes of operation. And you can see these at these points here and here we have ZVS and ZCS. So in fact, what happens is interesting that the body diodes of the MOSFETs will turn off on ZVS and ZCS, zero voltage switch. Normally, this is very good for us. Normally, because MOSFETs, they have internal diodes. So if we turn them off, power MOSFETs, right? If we turn them off at hard switching, if we do hard switching there, what happens is we cannot use MOSFETs. Because MOSFETs diodes, they do not have very good reverse recovery characteristics. So then we should use thyristors. However, if we can make sure that the body diodes of those MOSFETs are turned off with ZVS and ZCS, we can use MOSFETs. In the case of, in this mode, as you saw, even though we turn, the diode will turn on in infinite current and voltage. However, the turn off is in ZVS, ZCS. So we can use MOSFET. That's why we would like to focus on this mode of operation to make sure that we will be able to use MOSFETs. So the different modes of operation, as I mentioned, there are 4 modes of operation, depending on the current waveforms and voltage waveforms across the switching components. We would have these modes. And the interesting thing is only these 2 modes, when our switching frequency is very close to F0 or above F0, those are the cases that the body diodes of the switches will turn off with ZVS and ZCS, and we can use MOSFETs. In the other conditions, we need to use thyristors. And now what is the issue with the thyristors is the fact that thyristors are limited. First of all, they're bigger. Second of all, their efficiency is low. Third of all, the thyristors are limited by their switching frequency. So we cannot push our circuit in high switching frequency. And then if we operate in low switching frequency, the components will be bigger. We need to design like transformer will be bigger and passive components. So now I want to look at so we looked at the circuit, how this operates, right? Now let's look at how we can analytically analyze this circuit. Yeah.
Just a quick question. If you can get closer to the zero voltage, zero current switching, is there enough of a savings in, say, power dissipation that you could save on cost and weight of heat sinks?
Exactly. That's what we want to do. That's a completely correct point. That's what we want to do. Now, so looking at the same circuit and looking at this voltage here is going to be either VDC or 0, depending this voltage on here, VA here. If this switch is on, it's VDC. If this switch is on, it's 0. And then the voltage in this part of the circuit, in fact, we can find an equivalent resistance, bring it to the other side of the transformer, multiply by the turns ratio, right? See, so we can say this is the equivalent circuit of this. If we can find out a proper equivalent circuit, equivalent resistance for load. Now, we could do that by simplifying the system, looking on the first harmonic approximation. Only look at the first harmonic of this, step function. So we can look at, again, V input is a square wave form. We can look at the first harmonic, output also voltage, similar way, and then the current also similar way, and then RAC, this we can, looking at the first harmonic approximation, this is V first harmonic of the source voltage, output voltage divided by the first harmonic of the source current. And it will be defined by this resistance. Now, we can define this in this circuit the conductance of the circuit, the voltage gain of the circuit. We can look at the current gain of the circuit, and also we can look at the input impedance of the circuit, and also define a parameter called quality factor, which tells us what is the load condition. So if I'm working in the no load condition, R is infinite, so Q is 0. In the short circuit condition, this is 0, Q is infinite. So look at the characteristics of the circuit in different load conditions. So plotting these curves, they give a very interesting information to us. The fact is, when we charge a battery, any lithium-ion battery, but lithium-ion battery, normally we do it like constant current charge, and then we do constant voltage charge. For some period of the time, we do constant current, and then after we hit the maximum power of the system, we move to constant voltage charge. So the system will operate if we, for example, if we want to regulate the voltage at the constant voltage for some period of the time, the system will operate in a line. The operation of the system, because the load is always changing. This is a resonant converter which is being controlled by frequency modulation. And changing the frequency of the system, we will be moving from this curve to that curve, so we will be moving among the curves. So the control should be able to keep it in this case. Now, from short circuit to no load, which is this one, you see the maximum peak voltage happens somewhere between F1 and F0. Now, with a constant voltage, you would notice that the peak will move towards F0, and at this point, this system will operate as a constant voltage source. Whatever the Q is, we will operate as a constant voltage. What is the advantage of being able to operate in the constant voltage source point is that there's not going to be a lot of energy exchange between the resonant components, and the conduction losses will be smaller as well. So we would like to be close to here as much as we could, and slightly above it or slightly below it, not much. Because another point is, if we are operating based on the impedance, we can see these parts of the system, when we are above F0, system is inductive. In an inductive load, always switches turn off. The body diodes turn off with 0 voltage switching and 0 current switching, and that would help us to use MOSFETs. And then below here, it's capacitive region, and between F0 and F1 and F0, depending on the Q, we might be inductive, we might be capacitive. So we want to try to be in above a little bit F0 to make sure that we will reduce the losses as well. And in a similar way, if we are doing constant current charging, again, you look at, again, from F0 to F1, at this point, we will have a constant current case of operation. So now let me briefly explain what I mentioned before. This is in the case of a single cell lithium-ion battery cell. So first, we do constant current charging, and then we do constant voltage charging. Voltage is constant after that till we fully charge the battery. So this is for a single cell. Now, if we scale it up for a higher battery system, high capacity battery system, in fact, our charging will start from this point. Let's say, normally, if we have a battery between full state of the charge and low state of the charge, the voltage variation is within 20% of the full state of charge. So for example, if I have 4.2 volt when it's fully charged, the voltage will be 3.32 volt when it is not fully discharged, but 30% on the state of the charge. So in that case, this is my beginning point. Assume the battery is completely discharged. This is my beginning point. I start charging the battery. The battery is at 3.6 volt. This is the battery cell that we have assumed 3.6 volt is almost the. This is here, like we have 100 of them that's why we have 360. But in the previous figure, I had only for one cell. So this is our nominal port. It's a 3.6 volt cell battery. And then at this point, we have the turning point that we will go from constant current to constant voltage. And that's the end point when the current becomes 0. We would consider it's 1. So depending on each nodes that we have, we will have different points, turning points, and different current and different effective AC load and different, accordingly different Q factor. So based on these consumption, we can look at and designing on the resonant part. In terms of the boost part, in terms of the interleaved part, we want to see what is the best voltage that we can choose for the DC link capacitor. In terms of DC link capacitor, because our input is an AC signal, right? Is an AC because of the grid. So we can, if we are connected 240 volt AC phase, right? Then this is going to be the input voltage. And if we plot the duty cycle versus the phase angle, theta, right? We would notice, and this is the inductive current ripple, we would notice that this curve, which is the 622 volt case for the DC link, has much closer to duty cycle equal to 0.5. And in the case of the duty cycle equal to 0.5, as I mentioned before, we would have less input current ripple. So that's why we will choose DC link equal to 622 to make sure that we have we are closer in our operation to the DC link voltage, and we'll be able to reduce the current ripple in our system to increase the total harmonic distortion. So based on these assumptions and this design criteria, we have designed this converter, and we have looked at the converter's operation in the system. So when we start from constant voltage charging, constant current charging beginning, we in fact start from Q begin. See, these curves are respectively, they show different points of start. Initial point, turning point, and then stop point. So at Q begin, Q turn, Q num, and then Q end is there. And then this is Q short circuit. Another point which I forgot to mention before is that during short circuit, we need to have a power management for the battery charging system. So the power management would move the operating point from around this to somewhere here. Somewhere here, because at that point, what happens is the impedance of the system increases, so we can limit the short circuit current. So that's also another point that we need to look at when we are choosing the parameters. So in constant current charging, we would see the constant current charging will happen like that. At the beginning point, in our case, is 7.6 kilowatt. 7.6 kilowatt is equivalent to 19.1 amp if we divide it by 420 volt of the voltage of the battery. That 19.2. So we will try to regulate it constant current of 19.1. So from the beginning to turn point, the switching frequency will change from 238 to 1691. And then at the turn point, when we switch to constant voltage charging, we will move to this point here, and then we'll stay in the constant voltage at 420, and then this is the point that we will end our, see, this is the ending point of the system. So this is the way that we need to control. So this project, we are continuing this project. We're working on it. We have done some also analysis in terms of the simulation, seeing the numbers that we have achieved. Total harmonics distortion of 3.6% is very good. Power factor of over 0.99 is almost 1, is very ideal, and DC link ripple is very low. And we have done some simulations also here, showing the operation of the system depending on the different beginning point, nominal point, and turning point. And the switching short circuit frequency, as I mentioned, we will be moving to 450 kilohertz. Now, this project, we are right now continuing this project, and we are building this. So another point is that we are trying to build this converter using silicon carbide wide bandgap devices, so that we can even go further higher frequency. Because, I mean, we can easily go 200 kilohertz with silicon carbide material, and that would reduce the size of the passive components for us. Now, in parallel with this, we are looking at how we can integrate that charger that we had for this battery with the DC-DC converter, which is between the energy density battery and the propulsion machine, with this, and then only put one of them. That is further reducing the size and increasing the power density of the system. So in fact, we are combining these two to get much higher power density. Now the point is that converter now not only should be capable of doing all that modes that I explained, but also should be able to provide the functionality of this DC-DC converter. So step the voltage up for this propulsion machine during acceleration and step it down during regenerative braking. So the additional modes will be included in this mode. As you can mention, it should be able to do the charging, stepping up during cruising, just normal providing power, and also deceleration. So we designed this converter in our lab, and this is a integrated converter. It's a 15 kilowatt converter, and it uses one inductor only because it's combined two of these power electronic interfaces. So only one magnetic component. However, in the other combustion topology, they have two. So you can see we have only one inductor. This is here, only the transfer inductor, which I have used for both of them. And you can see this is the universal kind of system which operates with different input voltages and the wide battery voltage. Transferable power is like maximum 15 kilowatt. In case of charging, it is up to close to 8 kilowatt, not more than that. This is transferable between the DC converter. The power density in this system is 5 kilowatt per kilogram. It is not like exactly similar to what DOE wants right now. DOE wants something about 10 or 11 kilowatt per kilogram. But this is something we've built only in the lab. It's like something, a prototype. Easily, if we eliminate these things and come up with a very nice, if a manufacturer can definitely get this number with the same design, with a more like a nicer design. So this is definitely possible, and we expect that we will get it. Interesting thing, in boost mode of operation, we get up to 96.6% efficiency, total harmonic 4.5, and power factor more than 99%. These are some of the experimental results that we have achieved, and you can see that in 1.8 kilowatt charging, the results that what we are showing here is for a little bit lower power, because in our lab we are limited. We cannot go up to much higher power levels. So we have done our tests with like about 1 to 2 kilowatts tests. So you can see that this is the efficiency curve. All these are experimental data. They are not simulation. You can see maximum efficiency at charging goes to 91.6, yes, at charging. In propulsion boost mode, it goes up to 96.6. And in the propulsion and the regenerative braking buck, it goes up to 94.1%. So in summary, so far, what we did, I explained the design consideration for a level 2 PEV charger, condition of the interleaved topology, isolated LLC converter, operation and the design consideration. And then I a little bit explained about the integrated single-state charger and propulsion, and I mentioned the prototype that we mentioned, and the efficiency that we achieved from this. Now, I a little bit want to talk about different subjects right from here on. That subject is more on a system-level way that, so it's still energy, a system-level way how we can reduce the size of energy storage system of electric cars. In fact, in majority of the current and upcoming plug-in electric car and all other cars, we have batteries as their energy storage system. The problem with high energy batteries is that high energy batteries, they have very limited power density. And the problem with high power batteries is that they need to be oversized to provide load power and energy demands. Most of the cars which are coming right now to the market, they are using high power batteries because they want to be able to provide enough power during acceleration and be able to absorb regenerative braking energy. But what happens is these batteries need to be oversized to be able to have a very high power density. Even I have read in an article that they are mentioning even they oversize up to 4 times, which is significant. Now, either case, if we use this or this, the battery's lifetime reduces significantly depending on the peak power which the battery is providing or absorbing. And battery is not capable of efficiently absorbing all the energy. And in the meantime, battery is not efficient when it goes beyond 80% state of the charge, or below some specific, let's say 30% state of the charge. So SuperCap can take lead on that part and improve the performance of the system as well. So we are looking at hybridizing batteries with supercapacitors. And this is a completely overall system level solution to this. The objectives are reduce the weight of the energy storage system composed of high energy battery, ultracapacitor pack, and DC-DC converter to less than 70% of the weight of a single high power battery alone. And while increasing the life of the battery by at least 25%. So we have a project going on, a small project going on with a company called Regenerative. They are a Rockville-based company, and they are building a new car called G2. This is a real car, but it's going to be in the market in 2014. And their car has 2 propulsion machines, as opposed to the majority of the cars that they have only 1 propulsion machine. The reason for that is, in fact, because they would like to have they have, first of all, a size constraint, because this is their initial prototype is being done on a Corvette. And a Corvette, because in front hood, you don't have a lot of space, so you cannot, if you want to put a big propulsion machine, it's going to be huge. So one reason is 2 propulsion machines, if you can stack them next to each other, it would be compact. And also, this will give us more reliability in the case that some of them doesn't work or fails. And also, efficiency of the system will be also higher. So we're working for this company to design a DC-DC converter here. And in the meantime, we have come up with this idea. If we can use this converter, normally in the cars, if you have this additional DC-DC converter and you have this charger, they are completely independent. They operate independently. So we have come to a point that we can integrate this and use a technique called active power filtering and eliminate one of those stages. The DC-DC stage that we had in the previously when I showed the charger, that LLC part, resonant part, we can eliminate that stage and use this converter and use this only we can reduce 30% the size of that converter too. I'm not going to talk about those things in detail, but I just want to give an overview of what is our research direction is. And we have done some analysis. This is not experiment, but just analysis that shows that if for that car, for G2, if we use only battery pack, high power battery pack, the weight will be about 500 kilograms. Now, if we hybridize it with supercapacitor and use high energy battery, not high power battery, we can reduce the weight to 320 kilograms total energy storage size. And if we use other kind of batteries, like there is a battery being produced by this company called NVIA. NVIA is one of the most famous companies because of their high energy density batteries. They have very high energy density, but they're not very promising in terms of high power. And we don't care. Our technology, we care about high energy. We don't care about high power because supercaps are very good in terms of high power. So if we use NVIA battery, as this curve shows here, this curve, the weight of the whole system can be less than 320 kilograms less than the 500. So significant weight reduction and improved performance and also improved life of the energy storage system. These are stuff that could have huge impact in automotive market, because right now the batteries are I can say one of the biggest concerns in automotive industry is batteries, energy storage systems, because energy storage system, they don't perform very well, and they're very expensive, and they're very heavy. So for this car, we have run simulation, and we have seen if we reduce the weight of the car by 14%, by reducing the weight of the energy storage system, we can improve the all-electric range even 17%. That's also another thing that we can achieve. So these are the advantages we can achieve from this system. Now, briefly, I will finish in 5 more minutes, so I promise. So another research area that we are focused on is power electronic energy harvesting for energy harvesting. And you can see the technologies that we are looking at is a little bit slightly different than what a lot of other research groups they have looked at. Majority of them, they have looked at the piezoelectric energy harvesting. So you can walk, and they have looked at, for example, helistrike. From helistrike, you can harvest energy. But we are looking at human body's linear motions. This is also kind of looking at, let's say, for example, hand swing, arm swing, or limb motion, or even as opposed to looking heel stroke, looking at foot horizontal motion, right? Or center of gravity up and down motion. So all these movement, they have a common point. What is the common about these things? That there is a relative movement between two parts. So if we can design an electromagnetic machine which is compatible with all of them, we could somehow reconfigure it and design for all the different, and integrate with different. We can integrate with your cell phone. We can integrate with your, it can be integrated with the digital camera. It can be integrated with PDA, with MP3 player, with all those things. So it has majority of applications depending on where we want to install it. And another uniqueness about it is if we use it for the backpack, if we integrate it inside the backpack of a soldier of the future, for example, or a field scientist, let's focus on that. In fact, not only it can be used to harvest energy and reduce the amount of the batteries that these people need to carry, but also it could potentially improve the human walking performance. Why? This is like kind of system level, again, solution. Power electronics is always system. The meaning of the power electronic is a part of system. Why? Because if you look at the human walking, you see when I have a backpack and walking with it, when my center of gravity goes up and down, right? This backpack comes up and down with me, right? But the point is, when my center of gravity is the highest point, the backpack weight is also, the impact that it has in my body is maximum in that point. If I can change that force, and as opposed to creating a detent force, give a push forward, momentum push to the human, when even you're walking in the hill, like in somewhere which is uphill, I can help the person to walk better, right? So that's another thing we're looking at, but in high scale, we're looking at how we can increase it. In the smaller scale, we're looking at integrating in different components that you can see, GPS, cell phone. And so the enabling part is the technology is in two parts. One, the device itself, one, the power electronic interface. The point is, most of these devices, energy harvesting devices, are designed to operate with one switching frequency, and they are very efficient in a limited bandwidth. But if we don't work in that limited bandwidth, the efficiency will drop. We have proposed the power electronic interface to be able to match the load, even if we are not operating that. So if I'm not in the switching frequency level, then we can move to load matching mode, and we can still maximize the amount of the power which we can harvest from the system. So the idea is these two parts, one, the generator, and one, this power electronic interface, and we have a recent paper on this as well. And last topic is the miniature power supplies for micro-robotic systems. Some of you have heard of the devices which are designed in Harvard or at UC Berkeley. They have designed this very small micro-robots. And one of the issues that they have is these micro-robots, for example, if they are, in this case, which is a piezoelectric-driven micro-robot, they need to have high voltages to operate. And the batteries that they can have on board is a very small battery which would provide 3.7 volt at most, right? However, the voltages that they need to operate is, for their excitation, is 200 volt. So we need to have an interface. They need to have an interface in between which converts that 3.7 to 200 volt. And if similar buck or boost we use for that, they're going to be big. So in the case of Harvard, they have designed, the state of the art right now is designed by a group led by Professor Robert Wood at Harvard, and they have, this is the specifications of their board that they have designed. It's a 90 milligram device, and it gets 38% efficiency, like 72% max efficiency they get in the DC-DC stage, and they have a DC-AC stage of 54%. Now we have been collaborating with Professor Sarah Bergreiter's group in here at Maryland, and we have designed another interface, which you can see is much smaller than what designed at Harvard. So this is the interface designed by Harvard, and that's the design we have designed it. So this can step up to 3.7 volt to 200 volt, and you can see it's only 31.5 millimeter square. It's very small, and it's 66 milligram only. It's very light, and it's a two-stage power electronic interface. And we are trying to work more in this area, and even reduce this size by half. 50% even less. So we're looking at different topologies that can give us direct DC to AC excitations. So recently we helped to organize the fall 2012 EV meetup at our campus. It was in November 11, and we had a lot of cars. Some of the students, they attended, and I guess they liked it. So we have the majority of the cars in our campus. We had Tesla Roadster, we have a Fisker Karma, we have Ford, we have Nissan Leaf, we had Tesla Model S, and many other cars. At the end, here at Maryland, we are developing milliwatt to kilowatt level highly efficient power electronic interfaces for a variety of system level applications. And thank you for your attention, and I'll be happy if there is any questions. And that's what the end of gas would look like. Thank you. Thank you.
When you said about the DC to DC converter before, you said you want to combine it with the charging station. Is that the same thing as the quick charge DC charging station?
No, totally different. DC, quick charge DC, they are directly connected across the battery. So if you look at Nissan Leaf, has two cords. One is for AC, one is for DC. So that from the DC charge is connected to the cord.
That's a lot faster.
It's a lot faster, yes.
But is it like more expensive?
It's big because the power level, when you look at, you want to inject 50 kilowatt inside the system. So it's big, the power should be sent. It's very, very complicated to be able to integrate it on board. But we're looking at different ways to do that even. Yes?
Do you mind if we talk about briefly about the micro-watt miniaturized power electronics?
Sure, definitely. So the question is that can I like?
Use different materials from your silicon carbide or GaN materials for that.
For micro-robotic application, no, we are not using silicon carbide or GaN. We are using some simple silicon devices because the reason to use silicon carbide devices is that in high power levels, first of all, higher switching frequency. Second of all, less loss in higher switching frequency, right? So we have used normal switches, and because we are not so much concerned about the size of the switch in the case. So those devices we try to use in automotive application. The point is, this device again can be small if we look at bare die devices. In case of the MOSFETs, bare die or package, it's not going to be significantly different. The most important thing is to get like a magnetic component. That's why if you look at the transformer that we have, in fact, I can show you here. This is the circuit that we've designed here. You can see the transformer is very small. You see, this is the package removed transformer. You can show like this is very small. You see, this is the transformer total. So, other questions from yes?
You mentioned earlier about the challenges, and one of the challenges you had on your slide was reliability.
Yeah, reliability. We most of our focus on addressing the reliability was to improve the life of the DC link capacitor. So using interleaved topology helps us to reduce the stress on the capacitor and improve that. So reliability should, from our perspective, is more like failure of the capacitor. So that we try to use the interleaved to improve the reliability.
So when you use those high frequencies, is there any issue with radio frequency interference?
We haven't studied that to years, but I don't think that's going to be in the same. What is the radio frequency like?
I actually don't know, but I saw
I don't know. Okay.
several kilohertz.
Yeah, we go up to like 200 kilohertz, but I don't know if 200 is just interferes with that. But that's the thing that a lot of people are looking at it. I don't think it's going to be interfering with that, but it's better to pay more attention to that. Yeah. Thank you. Yeah.
For the using your technology to integrate with like wireless power transfer.
That's one of our future research directions. That's one of the future. We would want to do that. We would want to look at the wireless charging as well. So that's definitely one of our research directions. Thank you. Okay, thank you so much for attending the presentation.